Here we go, welcome back to the DB2 lecture series. And let's continue our discussion of the main memory database systems MonetDB. And in fact, the BUTs, these ordered vectors of payload data in these binary association tables, these are RAM-based data structures. And this is where all the processing takes place. This is where all the processing takes place. All these operators, the mul operators like algebra, projection, they are operating over RAM resident BUTs. That's where all the processing takes place. If you would switch power off now, then of course MonetDB would forget the contents of all BUTs. They are stored in transient RAM. So to provide persistency, to keep BUT contents also across system switch off, system failures and so on, BUTs are stored and copied into persistent representations that live on disk, on regular HDDs or SSDs in the file system of your computer system. Before we can operate on these files, let's say here's a file F living on disk, having the contents of one of our precious BUTs. Before we can operate on these, MonetDB uses a particular UNIX system call, the mmap system call, which we provide the name of the file as one argument. And what mmap will do is memory map the contents of the file, memory map the contents into file into RAM, into a contiguous part of the RAM memory, of the transient memory, where we could use our mul implemented operators to scan the contents of these files, to operate over them, to just do query processing. So persistent files on disk, mmap them into the into contiguous space of memory, where we can then operate over the contents of the file. Okay. Let's take a closer look at this. It is quite interesting. This is an excerpt of the man page, of the manual page, of the UNIX manual page for the mmap system call. And I can only encourage you to use the man command, the UNIX man command, to actually look at the contents of this system call. You will find that it contains a lot of detailed information for developers who want to use mmap system calls in their C programs, for example. And looking at the mmap manual here, you can see that you will provide a file descriptor, Unix representation of the persistent file on disk that will store the BUT contents, mapping that file descriptor into contiguous, or the contents of the associated file into a contiguous space of memory. Okay, the address of that memory is will be returned here, and that's all that mmap does actually. The contents of the file are mapped one-to-one. No processing is taking place, no conversion is taking place. A one-to-one mapping of the contents of the file into RAM is performed, and that's quite remarkable, because you will see that other systems like PostgreSQL do a lot more work, to convert the on-disk representation of a table inside its heap file, for example, into the internal representation that we can then operate over. So the mmap idea and the mmap concept is a really mean and lean implementation of mapping the contents of a file into memory. MonetDB and other systems that use mmap rely on the operating system and its virtual memory capabilities to map even huge files. Even files whose size exceed the available RAM memory size are mapped into virtual memory, and the operating system performs page mapping and memory mapping so that we get the illusion that the entire contents of the file have been mapped into RAM. This is a task that is diverted and pushed to the duty of the operating system by MonetDB. Okay, so let's see whether we can peek inside these files and better understand how the representation of the BUT content and the BUT payload on disk actually looks like. And there is a command for that in the ML language, the BUT info command, that we can use to collect all the interesting details about a BUT, and also if it's a BUT that has a persistent mirror image on disk, we can also collect info about where we can find that particular file, and then of course we can peek into it. So let's try to do that. Let's try to do that with the A BUT that we have used in the last video, the A BUT that represents the A column of our SQL table unary. It's already bound to the mul variable A in this session. So what I can just use the BUT info command on the A BUT and then collect information about that. Actually, that information comes in the shape of two further BUTs that I'm assigning at once here using this parenthesis or tuple syntax. So collect all the information you can find about BUT A and then print it in the SQL session here, in the mul session actually. Oh, there you go. So lots of information that of course is again represented in BUT form. Eat your own dog food. So this is the information about the A BUT. Let's see what interesting stuff we can find here. For example, the BUT will represent 100 rows. That's fine. Okay, so the head column is of type void. We knew that. All head columns are of type void. The payload tail column is of type int. This A column is indeed a persistent BUT that has a persistent representation on disk, and that is something that we can read off here at this particular point. The sec pace, so the first off that has been assigned to the very first row is 0. We also knew that. Let's scroll down, let's scroll down, let's scroll down. Okay, all right. So further information. This is the size of the internal representation of this payload, and it's 400 bytes. That's 4 bytes per integer in 100 rows. That makes for 400 bytes of representation size for this particular BUT. Okay, that's nice. And this offset 36 actually shows us some information about the file, the operating system file that is used to hold the persistent information, the contents of our BUT, of the column BUT A. So I think it's time to have a look at this file. All right. So let's switch over to the shell. Okay. And see, where are we? Okay. So we can just use the normal operating system file system commands and check the MonADB directory. There's a data subdirectory there that will store all the files for the Scratch database, in particular the BUTs for the Scratch database. And now below that, in subdirectory 13 in file 1370.tail. All right. This should be the file that holds the persistent information for our BUT. And there we are. And indeed, it has a size of 400 bytes. There is nothing in this file but the 104 byte integers. No further clutter, no further meta information or something. This is just the raw data. Okay. Of course, we could look inside that file. We could just mmap it into RAM and then try to scan its contents and see whether we can actually find the integers 1, 2, 3 up to 100 in there. And to do that, I've created a C file, a C implementation that actually can do that for you. And that C implementation will of course use the mmap system call. So that C implementation first defines the path to the actual tail file. Let's see, that's 13. Okay, this is where the actual tail file should be found. All right, so let's scroll down to the main program. Yeah, what does it do? It will take that file name. It will take that file name and mmap that particular file name for us, it will return a pointer into memory, the tail map pointer. It will return a pointer to memory that will carry the 400 bytes. That we are talking about 400 bytes will also be returned in this tail size variable here. Okay, so this is the mmap system call. Actually, it's a wrapper around that call. If we look up the mmap file function, then you can see that I'm checking that this file is actually openable for us. So we open that particular file to obtain a file handle, check all kinds of stuff, whether we can actually read the file and so on. But once we have asserted that, we can use the mmap system call, on this file descriptor to actually open the file and map it into RAM for reading. Okay, and the pointer that is returned, is actually the 400 bytes of memory that we can use to access the contents of the file. And that's what we return here. Okay, so that would be that pointer of the file. What we then all have to do is to scan the contents of this particular memory and see what we can find there. And that's implemented in the scantail function. So the scantail function gets the first argument is just a pointer into memory. It will be a pointer, a vector, an array of integer values that we can simply scan. How many of these? That's encoded in the size parameter. And that's what we do. We just scan, we just iterate over this particular array, starting at address tail. We are increasing these offset, densely ascending offsets, starting from 0, 1, 2. We are scanning this vector file, and what we find there, we will interpret as integer values, which we can just print out. Okay, so let's check whether it's really the case that this file here actually contains the payload contents of our BAT. So let's switch to the shell and then enter the directory with all the C files. We will also find the C file in there, the mmap.c C file. Very good. Okay, so time to compile that. Okay, there's the mmap. The executable file will be called mmap. Okay, compiled. Let's execute that. And let's see what we can find in these 400 bytes. And yes, of course, we can find the contents of the payload of that column. The 100 integer values here, they all have been stored persistently in this tail file. We have mmapped it into memory just like MonetDB itself would do, and then iterated, scanned over the contents of this integer array. So that was really simple because this has been in BAT of integers. So looking at the type descriptor of this BAT here, it's indeed an integer BAT. And for the particular width of integers that we were talking about, tau equals int, that particular atom or scalar type in mul, the width of these elements in the file is just 4 bytes, as we said before. It's a fixed width of 4 bytes. The first row will have a 4-byte payload. The 100th row will have a 4-byte payload. It's super simple to peek into this representation of the BAT payload to access a value at offset I, for example. That's what depicted here. If A is the C array, the vector of values that we have just mmapped into memory, to access the ith value is quite simple. To access at the value at OID I at 0, and this is something that operations like algebra.fetch, bat.replace, and they're doing positional access. We are just using this I here as an array offset into A. We take into account that the H sec base might not be 0. It often is. Sometimes it's 1, as we've seen already. So we adjust our offset based on this age sec base of the butt. And this will be an integer that we can simply use to index into this particular array, just like the C programming language would be able to do for us. It would compute the effective address of the array A. It would perform this index computation. It would take that particular index multiplied by the width of the array elements, in this case 4 bytes. This will give an effective address to directly access, to directly get hold of the row at index I, or OID I, let's say. And this leads to very simple C implementations of operations like algebra projections that are scanning the contents, of a butt, as you've seen already. Such implementations are very simple C routines that use very tight, very simple loops over simple C arrays, and that's one main reason for the efficiency and for this raw speed that you will see when MonetDB handles the contents of butts. We will see that MonetDB's speed is quite remarkable, and it all derives from the simplicity of the data representation here. So this was talking about the very simple case of fixed with tail columns, but it could be a bit more complex, right? We could, for example, talk about butts whose payload is of variable width, for example, of string butts, of text butts. This would be such a butt. Of course, it has a virtual head column, but its tail column is populated with string values of variable width. What's the representation of such butts inside the MonetDB system, and how do the on-disk files look like for such variable width butts? Okay. To do that, let's switch back to the interactive terminal here. Okay, and for 1 second, let's leave the mul session here. Okay, bye-bye mul session, and let's open MonetDB SQL session again. Okay, there you go, a SQL session. And then we will create a table, a SQL table. It's called unary prime. We have seen it before, and the payload in that particular single column table will be string values or textual values. So let's create that table. There you go. And then use this logic here to fill that table with string values 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. You see I use this modulo operator here to have the string values repeat. Let's do that. The details of that query are not that particularly interesting, but we have inserted 100 rows. That looks okay to me. Let's see how the contents of unary prime now look. Okay, oh yeah, it's 100 rows. And we see the repeating string patterns 1, 2, 3, 4, 0, 1, 2, 3, 4, 0. That looks okay as expected. And these are variable width columns. Payload 3 bytes or 3 characters, even 5 characters, 4 characters, variable width payload. Okay, so how would that be represented inside MonetDB? Time to switch back to mul again. Bye-bye SQL. And back to mul. There we are. So let's get hold of the butt. Let's get hold of the butt that actually stores and represents the column A of this new table unary prime. Okay, so we know these commands already. Initialize talking from mul to SQL, then get hold of the A, the column, the butt for the A column of this unary prime table. You see, I'm talking about the unary prime table here, and I'm talking about its A column, and that's the butt I want to get hold of. I will do that. Okay, so first let's see whether we got what we expected. Yes. That's 100 rows in this particular bud and a variable width payload column. Okay, how is this internally represented? Okay, get information about this bud and then print it. Lots of stuff to see here. Let's see. Yes, it's a string bud. It's a bud with variable text values in the tail. Okay, what's its size? I'm interested in its size. What's the size? The size is just 100. So 100 rows, in this case, only occupy 100 bytes. Okay, scrolling further down. But now we see that there is more than one file involved, more than one file name is listed. We see the expected tail in its file name, that's what you see here, but there's a different file involved, the theap file, and it has also been assigned a file name in our file system, so two files are used, the tail file and the theap file, to represent this bud of variable width. Let's switch back to the slides for a minute and see how the whole thing works. So that's the setup. We have allocated, or we have created such a bud with variable width column. Its internal representation is split up in two parts. We have one column or one column file of offsets that point into a string dictionary. So the actual string values live inside the string dictionary. 201 is represented in this dictionary only once. We are reusing these values several times, up to 100 times in the A column of the unary prime table, but each unique string value that occurs is represented only once in the string dictionary. That makes for some nice compression and some nice compaction, because if we have repeating string values in such a SQL table, and that's often the case, then we will only represent them once inside this internal representation of MonetDB. Each of these string values has been assigned an offset inside the string dictionary. 2 is found at offset 0. We append a 0, a null byte here to indicate the end of the string. So 0 will be found at offset 4 and 1 will be found at offset 9. Okay, and these 0, 4, 9s are the offsets that we find in this first column file. So the 0 value is the 0 string is actually represented by this offset 4, which points to the 0 string in the dictionary. Okay, 1 is represented by offset 9, which we'll find in the dictionary to carry the value 1. And of course, this string 1 is represented by the same offset, and it will also lead us to the same entry in the string dictionary. So just 3 strings are sufficient in the dictionary, are sufficient to encode the entire contents of the tail payload column, given that we have such a column file and offset file that is that's pointing us to the right positions in the string dictionary. And this is also the answer to why the representation of the tail file, this is the tail file of the payload column of our unary prime column A, only occupies 100 bytes. It's just 100 integer offsets, 100 offsets that are pointing in the associated string dictionary. Each of these offsets has a value smaller than 256. Single bytes are sufficient to point in the appropriate string dictionary. And the theap file is actually where the string dictionary resides. The theap file is actually a bit larger. It occupies 16384, so 28 kilobyte blocks here. We will see that the first 8 kilobyte blocks is actually unused, but this is where the actual string values reside. This is where only 100 integer offsets into this string string dictionary are held. And if we switch back to the terminal here, then let's see if this is actually what we are seeing in the file system too. So we will look at the file 14.7 tail. These are 100 bytes of integer offsets in the tail file, and in the theap file this size of data, so a bit more than 1 kilobyte, 8 kilobyte of data. Actually, as I told you, the first 8 kilobytes are unused, so the string dictionary is really tiny. This is only slightly larger than 8 kilobytes, and these few bytes they are sufficient to encode the 100 string values that we find in column unary and column A of table unary. Okay, we could peek inside this file, and let's see what we can find there. Yeah, okay, all sorts of gibberish, but we certainly find the strings 1, 2, 3, 4, 0 that we have inserted into the A column of table unary prime. So the data is there in some form. And just like we could write a C program to scan a normal tail file, we can write a C program that scans the tail and heap files, for a bud that has the variable with payload or tail column. And this C program is called heap.c, and have it here in my editor. We could just configure that very quickly. Of course, this C program would talk about two files: the tail file holding the offsets, and the heap file holding the actual string dictionary. So let's fill in the actual file names here and path names. 14. Okay, so much for that. So the main program will map two files. It will map the tail file and it will map the heap file, and it will obtain tail map and heap map pointers that we can then use in the scan tail function to actually walk over the tail file, collect all the offsets, and use these offsets to point into the heap file or in the memory mapped heap file to extract the real strings. And that's what you will find in the scantail function. Let's see the scantail function. Very simple. The scantail functions gets two arrays. One array of integer offsets that I can use to point in this array of character data in this string dictionary. Okay, and that's what I'm doing. I'm iterating over all the offsets that I'm finding in the tail file. Here's one of these offsets, and I'm printing them here. And then I'm using that same offset to point into the heap file at this particular offset. You see that there is another constant offset I have to add here. This is actually the 8 kilobytes. This is 8 kilobytes. The 8 kilobytes I was mentioning, the first 8 kilobytes do not carry string dictionary data, but MonadDB internal data. But starting at this offset, I can point into the heap file and just extract the string value. And that's what I'm printing here. It's a normal string value that I'm printing here. Okay. So let's see whether we can compile that. This is my session again. And we are back in the directory with the C files. This is my C program, and I could compile that now. Okay. The program is heap.c. The executable will be called heap. compile and execute. And there you go. 100 entries. 100 entries lead to 100 offsets found in the tail file. Following that offset will lead me to a string I can find in the heap file or in the string dictionary, and I'm just printing it here. This reproduces the variable width payload column of the A column of the SQL table unary prime. A very compact, very clever encoding of the variable width data inside butts inside MongoDB. So much for that. Okay, so that actually is quite a step already into the internals of MongoDB, and everything that follows is a consequence of these cool design decisions of representing fixed width data just in C arrays, of representing variable width data using these dictionaries, and having very simple C routines, tight loops that iterate over the contents of these fixed width element vectors. Okay, that's the stuff that is will be had in the DB2 lecture, and I cannot wait to explore this together with you. Bye bye, take care.